we have already discussed about classical harmonic oscillator, that is simple harmonic motion. We have seen that if a particle moves back and forth about an equilibrium position under the action of a restoring force, which is always directed towards the mean position of motion and is proportional to the displacement of the body from the mean position, then the motion of the particle was termed as simple harmonic motion. And the law was governed by the Hooke's law, that is, the restoring force was proportional to the displacement and was oppositely directed to the displacement. So F was proportional to minus x. So F equal to minus kx, k was called the force constant. Now, if we apply the Newton's second law, that is force is mass into acceleration, then m d2x dt2 is equal to minus kx. From where if we write k by m as omega square, we get the differential equation for simple harmonic motion d2x dt2 plus omega square x equal to 0. And what is omega is called the angular frequency or natural frequency of vibration. It was root over of k by m, k being the force constant and m is the mass of the object. Now, as we know that the motion of a bob of a simple pendulum is an example of motion of classical harmonic oscillator, and the features of SHM are: the restoring force acting on the particle is proportional to the displacement, the restoring force is directed opposite to the displacement of the body, the motion should be periodic in nature, and the motion can be mathematically expressed by a sine or cosine function, which we shall see. When we were discussing about simple harmonic motion, we have solved the differential equation d2x dt2 plus omega square is equal to 0, the differential equation of SHM. We solved it in detail and we obtained the solution as x equal to a sine omega t plus phi, and the quantity a is called the amplitude of motion, that is the maximum displacement from the equilibrium position. Omega is the circular frequency, and the total term inside the bracket, that is omega t plus phi, is called the phase, whereas phi is called the initial phase of motion. And by using this value of x, we have already determined the expression for velocity, expression for acceleration, expression for kinetic energy, as well as the potential energy. So what was the expression for kinetic energy? It was half m omega square a square minus x square. For detailed calculation, you may see the video of simple harmonic motion, which is already uploaded. The kinetic energy is given by half m omega square a square minus x square for any arbitrary position x, where a is being the amplitude of motion. Now look here, where the kinetic energy is maximum, at x equal to 0. So in the right hand portion you can see the graph. The graph marked by the red color gives us the graph for kinetic energy with respect to the position x. Now look here, at x equal to plus minus a, it is 0, and at x equal to 0, that is at the equilibrium position of motion, the kinetic energy is maximum. It is half m omega square a square. Now we also obtained the expression for potential energy, which was half m omega square x square. And if we use omega equal to root over of k by m, then we can also write it as half kx square. And if we plot it with respect to x, look here, it is 0 at the position of equilibrium, and it is maximum at the amplitude position, that is at plus minus a. Look here, the blue line in the graph represents the potential energy of a system executing simple harmonic motion. And if we want to find out what is the total energy of a body executing simple harmonic motion, that is the summation of kinetic energy and potential energy, we just add these two, kinetic energy and potential energy expression, and we obtain it half m omega square x square. And look here, half m omega square s square, where m is the mass, omega is the circular frequency, and a is the amplitude. This is the constant term. So for a body executing simple harmonic motion, the total energy is constant or conserved, and look here, the energy is proportional to the square of amplitude. That is, energy is dependent upon the square of amplitude. A. So this is the expression of energy for a classical harmonic oscillator. As we have discussed that we can consider a classical harmonic oscillator. Suppose it's a mass m attached to a spring of spring constant k, and the motion is governed by the Hooke's law and due to its elastic property, and we can express the potential Vx as half kx square, what we have seen earlier, and the motion is governed by F equal to minus kx, which we have seen earlier. But in practice, there is no such thing as a perfect harmonic oscillator. That is, if we stretch the spring too far, and at a certain point the spring is going to break and the Hooke's law completely fails. So, what is the way out? Now look here in this figure, a potential is plotted with respect to x, a potential function Vx is plotted with respect to x. Now look here, for practically for every cases wherever there is a local minimum, we can express the potential as a parabolic function, where in the neighborhood of a local minimum. So from figure, if we consider the point x equal to x naught, and if we want to expand the function Vx in Taylor series about the point x naught, so we have from your mathematics you know that the Taylor series expansion of a function of x Vx about the point x equal to x naught gives us Vx equal to Vx naught plus V prime x naught x minus x naught plus half V double prime x naught x minus x naught whole square plus dot 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 higher order terms. That is, here V prime x naught gives us the first order derivative of V at the point x naught. V double prime x naught gives us the second order derivative of V taken at the point x equal to x naught. So this is the Taylor series expansion of a function Vx about the local minima x naught. Now if we consider about V at x naught, it is a constant function. As it is a constant, this does not change the expression for the force. So we can just ignore this function Vx naught, and as we know that the potential Vx has a minimum at the point x equal to x naught. So what is the condition for maxima or minima? You know from your class 12 mathematics knowledge that the first order derivative, that is del v del x, that is V prime, which we have designated here, that the del v del x at the point of x naught should be 0. So the second term here V prime x naught is, if 0, the second term also vanishes. So we have only the third term, and if we neglect the higher order terms because the x minus x naught term is small, we can neglect the higher order terms. We have Vx equal to half V double prime x naught x minus x naught whole square. If we write k equal to V double prime x naught, as it is a constant and it is evaluated at that particular point x naught, so we have Vx equal to half k x minus x naught whole square. Look here, it is again just like the potential energy function which was used for a classical harmonic oscillator. So we can say that practically any potential can be approximated to a parabolic function in the neighborhood of a local minimum, which we have shown in this case. So we have the expression of potential energy for a harmonic oscillator, half m omega square x square, or you may write it as half kx square, as omega is root over of k by m. So the main task of quantum mechanical problem is to solve the Schrodinger equation, and we know the Schrodinger equation is given by minus h cut square by twice m d2 psi dx2 plus vx psi x is equal to e psi x. This is the time independent Schrodinger equation which we have discussed in our earlier class, where h cut is the Planck constant divided by 2 pi and Vx is the potential of the system. For this case, for the case of quantum harmonic oscillator, Vx is nothing but half m omega square x square. So if we put Vx in the expression for time independent Schrodinger equation, we have the equation which is written in the blue color. It is minus h cut square by twice m d2 psi dx2 plus half m omega square x square psi x. This is equal to E psi x. So this is the Schrodinger equation for a quantum harmonic oscillator, the time independent Schrodinger equation, which we have to solve. The solution will give us the wave functions, the ground state, the first excited state, and so on, the wave functions and the energy eigenvalues corresponding. This is a quite complex equation, and this equation can be solved by adapting the two different methods. The first one is power series method, which is rigorous calculation is required for power series method, and the second one is algebraic method or ladder operator technique, where by using ladder operators, that is by using operator method, we can solve this equation, and by solving it we can obtain the expression for the wave function of the different states and the energy corresponding energy eigenvalues. If we solve the Schrodinger equation, then we obtain this wave function. Some of the wave functions are given here, and the corresponding energy eigenvalues of that particular state are given also. You can see here the ground state wave function. Look here, it is psi naught x m omega pi h cut to the power 1 by 4 e to the power minus m omega by pi h cut x square. This is the ground state wave function, and the ground state energy is given by E naught is equal to h cut omega by 2. And if we go up in energy, the first excited state, then energy becomes 3 by 2 h cut omega, and the corresponding wave function, it becomes more complex. And if we consider the as the first excited state and second excited state and so on, the energy of the nth state can be expressed at E equal to n plus half h cut omega, where n is an integer. For the ground state, n equal to 0. For the first excited state, n equal to 1, and so on. From here it is clear that energy cannot have any arbitrary value like classical harmonic oscillator. It should have some particular value which is n plus half h cut omega, and it should be quantized. So for quantum harmonic oscillator, the energy should be quantized. Here we have plotted the energy states, that is, as we go up with quantum number, that is n equal to 0, n equal to 1, n equal to 2, the energy is also E0, E1, E2 are according to the relationship n plus half h cut omega, and the classical energy half x kx square, which is parabolic in nature, which is also plotted. Look here, the energy expression, all energy states are equally spaced by a difference of h cut omega. So from here we can infer that the quantum mechanical oscillator, the energy is quantized, which is different compared to its classical counterpart, where the any value of energy was possible. Now for the wave function, the first 4 states are plotted. Here is psi 0, psi 1, psi 2 and psi 4, psi 3 here are plotted, and their corresponding probability density, that is mod of psi square, that is also plotted with respect to x, and the position distribution is also different here. Look here, as the probability of finding the particle outside the classically allowed range is not 0. Look here, the value of psi as a finite value outside the potential half kx square. Look here, it is non-zero. So the value of probability of finding the particle outside the classical allowed range is also possible for quantum harmonic oscillator, which is a different characteristic compared to its classical counterpart.